Dear students, let's learn more about this particular chapter, electric potential and capacitance. In that we have already learned about the device capacitor, and the next important topic related to the capacitor is combination of capacitors. To combine capacitors, we need a minimum 2 capacitor, and any number of capacitors can be connected. And when we do the connection, the combination is basically of 2 types. One is a series combination of capacitor and the other is parallel combination of capacitors. And one more, mixed grouping, where you can connect few capacitors in series and the rest in parallel, but the basic combinations are only 2. Series combination. Now, what do you mean by series combination? Series combination is also called as end-to-end combination, where we have one capacitor having 2 terminals, and let C1 be the capacitance. One end of it join to the other like this. This is second one. Take one more, you can join like this. Third one, this is C3. So, this is called series combination, also called as end to end. End of one is connected to the end of the other. This is called end to end. So, here I have connected 3 capacitors in series. Now, this entire system, now it acts like one single capacitor, just like if I take 3 forces, I can replace them by one single. And what do we call that one single? It's called resultant of these 3. Similarly, these 3 capacitors which are connected can be replaced by one single capacitor, and this is called effective capacitor, or is also called as an equivalent capacitor. So, equivalent capacitor is that capacitor which produces the same effect as that of the combination of the capacitor. So, 3 can be replaced by 1. So, that is why this is equivalent, this single. And effective capacity of that is a CS. So, what is C1, C2, C3? Individual capacities. And when that combination, it acts like one single capacitor. What is the capacity of that? CS. S stands for series. Now, what is the relation between C1, C2, C3 and CS? So, that is what we are going to derive, so in the form of derivation. Now, to understand this derivation, so first we need to understand the combination, property of the combination. And to understand the combination, this set of capacitors has to be connected to a battery of potential difference V. So, I have taken 3. For the derivation purpose, we are going to take 2 capacitors. And moment we connect capacitor to the battery, these capacitors are get charged. So, this becomes a plus, this becomes minus, plus, minus, plus, minus. Every capacitor is get charged. And in series combination, the charge on each capacitor is same, plus Q minus Q here, plus Q minus Q, plus Q minus Q. Irrespective of their capacities, the charges are same. That is the property of the series combination. But potential difference across them is not same. It is a V1, V2 and V3. For the simple reason that C is equal to Q by V. You can see their capacities are different. Charge is same. Therefore, potential difference has to be different. Capacity and the potential difference has to be different. Okay. So, this is the series combination of the capacitor. So, let us take the combination here. So, this is the circuit. See the circuit now, so that we can derive the relation. So, I have taken only 2 capacitors. First capacitor and second capacitor, having capacity C1 and a C2. Potential difference is a V. Both the capacitors, they get charged equally. You can see plus Q minus Q plus Q minus. Charges are same on both the capacitors. Potential difference is not same, which is V1 and V2, such that V is equal to V1 plus V2. So this is the first equation. V is equal to V1 plus V2. Now what is this? This is equivalent capacitance. And in the case of equivalent capacitance, the capacitance is CS. What about the charge? The charge is same. It's not these two charges will get added up. No. The charge on individual capacitor and the charge on the equivalent is also same. Plus Q minus Q. So this has to be same. It's equivalent, right? Okay. So now you take the first capacitor here, first one. Relate these three variables. What is the relation between C, Q and V1? C1 is equal to Q by V1. Correct? That is the relation between capacity, charge and the potential difference. What about the second capacitor? C2 is equal to Q by V2. Check this, important. See, Q is same, charge. Now tell me from this, what is a V1? Rearrange. What is V1? V1 is equal to Q by C1. From this, what is a V2? V2, Q by C2. Clear? Now refer the equivalent capacitance and then relate all the three variables. CS is equal to Q by V. Correct? CS is equal to Q by V. So from this, what is a V is equal to? V is equal to Q by CS. So basically here we have found V1, we have found V2, we have found V. And that's why I'll substitute here in 1. What do we get? V is equal to Q by CS. What is V1? Q by C1 plus Q by C2. And Q is common, right? So that will get cancelled. So what we get is 1 by CS is equal to 1 by C1 plus 1 by C2. So this is a relation between the effective capacity of the series combination and that of the individual capacitor. 1 by CS is equal to 1 by C1 plus 1 by C2. If there are three capacitors, write like this, no? 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3, if there are 3. If there are 4, add one more, plus 1 by C4 and so on. What we have derived is for two capacitors only. So in series combination, which quantity is same? Charge on each capacitors are same. So that is the point which you have to remember. So we have few more equations related to the series combination of the capacitors. So that will analyze. So hope this, and this question has appeared twice in the examination. So definitely an important derivation for 5 marks. Okay. In series combination, first one, for n capacitors. See, for two capacitors we derived 1 by CS is equal to 1 by C1 plus 1 by C2 and so on. If there are n capacitors, just extend it. 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3 up till 1 by Cn. Okay. The second, for two capacitors of capacitance C1 and C2. See, when we get 1 by CS is equal to 1 by C1 plus 1 by C2, we can further simplify 1 by CS. Take LCM here, you'll get C1 into C2. This is C2 plus C1. Correct? So I wanted CS, no? So CS is equal to C1 C2 by C1 plus C2. So this is how for two capacitors, this equation and this equation both are same. Okay, they are the same. It is just rearranged. That's it. Okay, so that's for two capacitors. Straight away we can use CS is equal to C1 into C2 by C1 plus C2. Next, for n identical capacitors, each of capacity C. Now if the capacitors are identical, then we can write like this: 1 by CS is equal to 1 by C plus 1 by C plus 1 by C. Imagine if there are three identical, then we get 1 by C plus 1 by C plus 1 by C is nothing but 3 by C. Or what is CS is equal to C by 3. C by 3. Okay, that is for 3. For n identical, C by n. So that is what the formula is. So if the capacitors are identical, then the effective capacity is given by CS is equal to C by n. Next, energy stored in a system of capacitors. So we know that the energy stored, in the system, energy formula, energy stored is given by half CV square, half QV, half Q square by C. These are the three different formats. So I'm going to use one of the format, half CV square. It's a USS stands for here series combination. Half into CS again, effective capacity of the series combination, and V is the potential difference across the combination. So that is the energy stored in the entire system, okay, not in individual capacitor, but in the entire system. What is the energy stored? We can find using this particular formula. So hope you have understood the different formulas. So we are going to use them while solving the numerical, okay. All right. So let's try one numerical based on the series combination of the capacitors. So statement goes like this: two capacitors of capacitance 600 picofarad. So I'm going to write here. So this is two capacitors. First capacity C1 is a 600 picofarad. Pico means 10 to the power minus 12, and the other is 900 picofarad. So C2 is a 900 picofarad. Are connected in series across a 200 volt supply. So V is equal to 200 volt. So here potential difference is V1 and this is V2. The charge is same, plus Q minus Q, plus Q minus Q. Then we have equivalent, which we call it as CS. When connected to the same battery, charge remains same, plus Q minus Q. Okay, so let's see what are the various options. First one, calculate the effective capacities of the combination. So choice 1, effective capacity. How do you find effective capacity? CS is equal to C1 C2 by C1 plus C2. What is C1? 600 pico 10 to the power minus 12 into 900 pico again 10 to the power minus 12 divided by C1 plus C2. 900 plus 600, which is 1500, and the common is a pico again 10 to the power minus 12. So this will get cancelled here. So let's find the answer there. So we have 900 into 600 divided by 1500, which is 360. 360 into 10 to the power minus 12 is there, right? In 10 to the power minus 12 farad. So that's why it's a 360 picofarad. Okay. So that's the first option that we calculated. So let's go for the second option. The total charge stored in the system. See, total charge stored in the system is nothing but Q. So CS is equal to Q by V. CS is equal to Q by V. So from this I can find Q. QS is equal to CS into V. CS is here 360 pico 10 to the power minus 12 into V. V is 200 here. So that will be 36 2s are 72, then 102030. So 72,000 into 10 to the power minus 12, 10 to the power minus 12. So this will be 72000 pico coulomb. Okay, so that's the charge, 72,000 pico coulomb. So that's what the option that is asked. Okay, let's see the next option, third one. Potential difference across each capacitor. Okay, and yeah, so potential difference across each capacitor. So that's what is given. So what is the potential difference across each? So potential difference across each here is this: V1 is equal to Q by C1. Q is how much? 72,000 pico 10 to the power minus 12 by C1 is 600 pico again 10 to the power minus 12. So this will get cancelled, 2 zeros will get cancelled here, and then we have this is 12 6 are 72, so 120, we get 120 volt. Similarly, what is the value of V2? So V2 is equal to Q by C2. Q is 72,000 into 10 to the power minus 12 divided by, next is 900 here, 9 into 10 to the power minus 12 again. So this will get cancelled, 2 zeros. So here 9 8s are 72, we will get 80 volt is the answer. Okay. So we have found the various options. You can see it's a application of the theory that we discussed, and two capacitors when connected in series, we can find the charge. We can even find the energy also. Suppose if they ask energy, then U1 is equal to half C1 V1 square. Okay, if they ask energy here, and the energy, what is the energy stored in the first? Half C1 V1 square. then you can find U2, energy stored in the second, half C2V2 square. And if they ask energy stored in the system, then you can add these two, U1 plus U2. US is equal to U1 plus U2, or you can even use the formula half CSV square. So these options are not asked, but still, in case if they ask, this is the way to find the energy stored in the combination of the capacitors. Okay. So hope this combination and the numerical is clear to you all. So we have one more combination which is called parallel combination of capacitor. Okay, parallel combination of capacitor. Again, this derivation has appeared once in the examination. What do you mean by now? Parallel combination. So in parallel combination, we draw the capacitor one below the other like this. Okay, and all the left hand side terminals are connected to one point. All right hand side terminals are connected to one point like this. So capacitors are said to be in parallel if they are connected between 2 points like this. If they are connected between 2 points, all the capacitors, you can see they are all connected between this and this. Then such combination is called as parallel combination of capacitor. And to that we connect the battery. Since all the capacitors are connected to these 2 points and even the battery is also connected, potential difference across each capacitor is same. You know, in series combination, which quantity was same? Charge was same, right? But in parallel combination, what is same? Potential difference across each capacitor is same. So we have household appliances like, you know, the tube light, the fan, there is a refrigerator, there is a AC, there is a TV, every device is there, right? Home appliances. And these are all connected in parallel combination, so that every device gets same voltage. The voltage that is required is nearly 230 volt. So that is the combination in which all the home appliances are connected. But for a home appliance, there is a switch, right? For every device there is a switch, and that switch is in series with the device. So switches are connected in series with the home appliances, but all the home appliances, they are connected in parallel combination. So in parallel combination, what is same? Potential difference is same across every capacitor. So now if you refer this equation, C is equal to Q by V, potential difference is same. Capacitance are different because one is C1, other is C2. When capacity is different, charges has to be different. That's why on the first capacitor, the charges are plus Q1 and minus Q1. Plus Q1 on the left hand side plate, minus Q1 on the other. Okay. Charge on the second, plus Q2 minus Q2. If there is a third capacitor, then it becomes a plus Q3 minus Q3. Fourth one, plus Q4 minus Q4 and so on. So in series combination, charge on each capacitors are same, whereas in parallel combination, potential difference across each capacitor is same. Now these two are replaced by one single capacitor, which we call equivalent or effective capacitor. What is the capacity of that capacitor? It is Cp. Now Cp, P stands for parallel combination of capacitor. What is the charge stored in that system? The charge stored in the system Q is equal to Q1 plus Q2. So this is the first equation. So what is the charge stored in the system? The charge stored in the system is equal to sum of the charge stored in each capacitor. So now refer the first capacitor. C1 is equal to Q1 by V. See the second capacitor, C2 is equal to Q2 by V. refer the equivalent Cp is equal to Q by V. So from this I can write what is the Q1? Q1 is equal to C1V. What is Q2? C2V. What is Q? CPV. Now you substitute this here. What is Q? CPV. What is Q1? C1V plus C2V. So that V will get cancelled. So you will get Cp is equal to C1 plus C2. Okay. So effective capacity of the parallel combination is equal to sum of the individual capacitor. In series combination, what was the equation that we got? We got 1 by Cs is equal to 1 by C1 plus 1 by C2. But here we get Cp is equal to C1 plus C2. If there is a third, plus C3, fourth plus C4 and so on. If there are n, plus Cn we get. That's how we get the equation. For n capacitor, Cp is equal to C1 plus C2 plus C3 and up till Cn. Clear? For two capacitors, Cp is equal to C1 plus C2. For n identical capacitor, Cp is equal to C plus C plus C. If I take 3 capacitors, that becomes a 3C. If there are 4, 4C. If there are n, nC. Energy stored in the system of capacitor. Up is equal to half Cp V square. So this is how we get the equation. So I'm going to write the comparison. So 1 by Cs is equal to 1 by C1 plus 1 by C2 and so on plus 1 by Cn. Cp is equal to C1 plus C2 plus C3 and so on up till Cn. For 2, Cs is equal to C1 C2 by C1 plus C2. For Cp, it is C1 plus C2. For n identical, Cs is equal to C by n. So here Cp is equal to Nc. Energy stored in the system, Us is equal to half CSV square. Here Up is equal to half CPV square. So this is how the equations are combined in the two cases, and these formulas are important. Derivation is important. This derivation has appeared once in the examination. Okay. All right. So these are the different equations. So hope you have understood both the combination. So keep in mind that in series combination, the quantity that remains same is the charge, whereas in parallel combination, any parallel combination, okay, not only capacitor, but any parallel combination, the potential difference remains the same across each capacitor. Okay, right. So let's again try a numerical based on this. There are 3 capacitors of capacitance. So I'm going to draw 3 capacitors, 1 and then 2 and then 3 capacitors are connected like this to a battery. So their capacitance are C1, which is a 2 picofarad, and C2 is a 3 picofarad, and C3 is a 4 picofarad. So what about the charge? Plus Q1 minus Q1 plus Q2 minus Q2 plus Q3 and minus Q3. What is the equivalent? We replace that by one single capacitor whose capacity is a Cp, and then the potential difference is a V. Okay, right. So first one, what is the total capacitance of the combination? First one, total capacitance is Cp, which is C1 plus C2 plus C3. We have to just add them. 2 pico, 3 and 4. So it's a 2 plus 3 plus 4. Pico is common, which is 10 to the power minus 12. So we get 7 plus 2, 9. 9 picofarad is the answer. Second, determine the charge on each capacitor if the combination is connected to a 100 volt supply. Do you have any other option? No. Okay. So here, potential difference across each is the same, right? It's a V, V and then V. So the charge on the first Q1 is equal to C1 into V. What is a Q2? It's a C2 into V. What is a Q3? It is a C3 into V. What is a C1? C1 is a 2 pico, 10 to the power minus 12 into the value of V. V is given connected to 100 volt supply. Yeah, V is 100. So this is 100. So this is 200 in 200 in 10 to the power minus 12, which is 200 picocoulomb. Okay. Then it's 3 value, right? 3 pico. 3 in 10 to the power minus 12 into 100, which is a 300 picocoulomb. And then 4 into 10 to the power minus 12 into 100 will give you 400 picocoulomb. So these are the charges stored. Even you can find the energy as well. Okay, like if you want to find the energy in the first, U1 is equal to half C1 V square, because the V is same, no, across each capacity. We don't write down V1, V2, V3. The energy stored in the second, U2 is equal to half C2 V square. Energy stored in the third, half C3 V square, and so on. How to find the energy stored in the system? Add them. U is equal to U1 plus U2 plus U3. Okay, or you can even find UP is equal to half CP V square. So like this, you can find the individual energy stored in the individual capacitor. You can even find the energy stored in the system of capacitor. So these two combinations are important. And dear students, we are almost at the end of this particular chapter. So soon there will be another test in this particular chapter. So that's why I start preparing, because there are a lot of derivations are there. So we'll have one interactive session prior to the test. So I'm going to announce the test soon. So that's why I start reading this particular chapter. So I'm going to continue the rest of the topics in my next class.